Hello, everyone. Let's start today's lecture. So last time we discussed about program efficiency, about how algorithms behave based on the input that they get while looking at the implementation of the algorithm. We took a look at several complexity classes and how we can identify which algorithm falls into which class. And there are specific characteristics of how an algorithm is written so that we can identify in which complexity class it will fall under, whether it will take a constant amount of time, no matter what the size of the input is, or whether it will increase with the same amount of time as the increase in the size of the input. That would be linear complexity. We also looked at some quadratic or polynomial complexity algorithms last time, where the size of the input increases the complexity of the algorithm or the runtime of the algorithm by a power of 2. For example, if n becomes 2n, the complexity of the algorithm would become 4n square. So why do we want to do that? And why measure the efficiency or complexity of programs or algorithms that we write? The reason for that is that we want to predict how they will behave as we change the size of our input. And this becomes very important when we are solving some real life problems. And secondly, when writing algorithms, we want to be clear about the choices that we make while writing them. We can write a simple program, but if it is behaving in a quadratic complexity, we have to look at it and think about whether we can reduce that quadratic or polynomial complexity to log linear or log linear to linear. And if it is behaving in a linear way, can we redesign the algorithm so that it behaves in a logarithmic complexity? But there are always some limits on the amount of time for any specific problem solving, and that would always depend on the nature of the problem. Some of the problems in computer science or when writing programs are inherently complex. And for example, if something is designed in a way so that every subsequent set of the problem or subset of the problem that we are trying to solve increases or doubles in size, then of course that would be exponential complexity, and some of problems fall in that category. We can never reduce the complexity of those problems, but there are always some intelligent choices that we can make in writing programs that will allow us to improve the efficiency of the programs. The basic principle here is that we want to identify the growth of the complexity depending on the input. When input size is increasing, we want to see how the program will behave. And we want to identify the growth of the program, not an exact measurement of the time required, but the growth of the running time as it relates to the input that is being received by the function or the algorithm. And what we are interested in is identifying an upper bound to the growth, and we can be lenient about it and say, okay, my upper bound on this algorithm is n square or polynomial complexity, and it will always fall within that upper bound. But we want that upper bound to be as tight as possible. So exact calculation or analysis of the algorithm is needed in order to identify that tight upper bound. And we also looked at the process of counting the operations within the algorithm to identify which part of the program is affecting the complexity or efficiency of the program the most. and that's what would actually become the complexity class of that algorithm. So in that way, we are always looking for the largest factors that affect the running time of the program. And we always look at the worst case scenario because we can never be sure whether when we are searching for an element, whether it's always going to be the first one or within the first half. We have to worry about or think about what the worst case scenario would be, and that worst case running time would actually be the complexity of the algorithm. Some recap about what we discussed last time. There is constant complexity where the running time of the algorithm does not depend on the input at all. There is logarithmic complexity, which grows very slowly in comparison to the size of the input. And then we have linear complexity where we are decreasing the size of our input by a constant amount every time. If, for example, we are trying to find an element within a list using a linear search, it would check every element starting from the first one all the way to the end. That would always represent linear complexity. Then there are some log linear algorithms, and we will take a look at them in detail in our next and last lecture of this class. We also looked at several quadratic complexity algorithms in our last session, and they usually happen when you have one nested loop within another one, both depending on the input that is coming into the algorithm. And lastly, we have the exponential running time or exponential complexity of a class of algorithms, which are very expensive to run, and in terms of cost on the machine or the time. And there are some problems that fall in this category that can never be reduced to a simpler problem. Towers of Hanoi was one example that we saw last time. Recursive implementation of Fibonacci also falls under this category. There is another very interesting problem that we will take a look at later in this class about generating the power set, and that is a very interesting problem. And that also has exponential complexity because the size of the result increases 2 raised to the power n times, where n is the number of initial elements in the set, and we will take a look at that. Some recap about the growth of different complexity classes. Here we have graphs that go where I have set the number of input elements to the same number for everyone, let's say 50 or 51. And we can see that the growth of constant it does not change at all. It remains at a very specific number. When it's log n, it increases very slowly. Only goes for 51 elements, it's somewhere around 5 point something, less than 6. When it comes to linear complexity, it increases to the same number or close to the same number or relative to the number of the input. If we have 51 elements coming in for an operation, we would be somewhere around that same number as well. Log linear, on the other hand, you can see it increases goes close to 300 for an input of 51, whereas polynomial goes all the way to close to 3000. And when it comes to exponential functions for an input of size 51, it reaches or approaches 6 raised to the power of 11. And we want to be as close to the top of the list over here as much as we can, because this is the running time that we are dealing with, and we want to be as efficient as possible. And you can see the growth of the running time increases for every next class of complexity based on the size of the input. And we want to be as high up in this list as we can when writing our algorithms. Now, moving on, constant complexity. There are not just a few examples or maybe parts of our code that can fall in this category. This is the category of algorithms where the running time or the complexity or the cost of the algorithm does not depend on the size of the input that it is receiving. It's doing some constant number of operations every time. This does not mean that we cannot have loops or recursive calls. We can have loops and recursive calls within our implementation for this kind of complexity class, but they do not depend on the size of the input. They are independent of the size of the input, or the implementation is independent of the size of the input. Even if we have loops or recursive calls, that would still fall under constant complexity. Next class is logarithmic complexity. We saw a very good example of bisection search in one of our early lectures, where we are trying to find a number between 1 and 100. And we saw that if we are trying to find a number between 1 and 100, we can do that in as many as 7 guesses, never more than that. And that is because we are dividing the size of our problem by half every time. And so it becomes 1 divided by 2 raised to power n, which eventually becomes log n complexity. And binary search within a list is one of those examples. So bisection search is very simple. What we In the last lecture as well, for linear complexity, we saw an example of searching for any element within a list. One simple way is to walk down the list, starting from one end and checking whether this is my element or the next one or the next one. And eventually we would find it somewhere in the list. If it is not present, we have to traverse all the way to the end, and that would represent our complexity of linear time, or n searches within the list for the worst case scenario. But is there a better way of doing this? If this list is unsorted, there is no other way than to check for each element. We also saw a better example in the last lecture where the list was sorted, and we would end whenever we identify a situation where element is either in the previous part of the list or is not present, because everything else after that is either greater or smaller than the element, depending on whether the list is sorted ascending order or in descending order. But the worst case scenario for searching linearly within a sorted list is also big O of n, or linear time. Is there a better way of doing it? Of course there is, and that would be using the method of binary search, or bisection search. And the simple algorithm is that we pick an element or an index within the list which is sorted, and that index is somewhere that divides the list in half. So let's say we check the middle element for our first guess. If that element is the one that we are looking for, then we say, okay, we are done. Very good. But if it is not present if it is not that element, then we check whether it is smaller or larger than what we are looking for. And depending on the answer, we would either discard the upper half of the list, or we can discard the lower half of the list, and effectively reducing the size of our search from full list to half in every subsequent call. So that way we are reducing the size of our problem by half every time. And this would eventually result in a complexity of log n as compared to the complexity of n. Or we can say, in other words, that we will enhance our algorithm from a linear complexity to log n complexity. So this is a method of divide and conquer, because we are discarding half of our problem size, and basically we are reducing our problem size to half in every subsequent call to this function, or every subsequent iteration, or every subsequent recursive call to the same function. So let's say we have n elements within which we are trying to search. We will search in the middle and discard one half of it. So in the second iteration or second recursive call, we would have n divided by two elements. We would do the same operation again, search the middle element and discard another half of this list. So on the third iteration, we are at n divided by four elements. If we go all the way to I steps, our problem size is now n divided by 2 raised to the power I elements. And we would keep on doing it until either we find the element that we are looking for, or the last remaining element is just one and it's also not that element. So even if we don't find the element that we are looking for in this list, using this method, we are only doing n divided by 2 raised to the power I searches or steps, which results into log n complexity. So for a binary search or bisection search, this is possible only if the list is sorted. Now, how much time does it take to sort a list? We will take a look at that in our next lecture, which is regarding searching and sorting. But we have reduced using this method. We have reduced our complexity from linear to log n, which is a considerable gain when it comes to cost and running time. Here's the simple implementation. Let's go through this one by one. We are checking whether the list is empty. If it is, of course, our element cannot be there, so we are returning false. If the list is of size 1, then we just check whether the element that we are looking for is the element in the list. If it is, then the result of this equality operator would be either true or false, and that would be our result. If not, then here's what we are where we are doing the actual division of our problem. We are saying that half is the middle of the length. We are doing the integer division here. So if the length was 100, 100 divided by 2 would be 50. If it was 99, then this integer division would give us the answer of 49. Because the answer would be 49 point something. We would discard the decimal elements and the integer result of half would be 49 in that case. So this is, if you remember, this is the slicing of the list. We are saying that start from 0, go up to the half. So here we are discarding the second half. In this slice, we are saying that start from half and go all the way to the end. So this is where we are using the second half and discarding the first half, depending on this search condition. Maybe I spoke the opposite in the beginning, but this is what we are doing. Discarding half of the list every time we call this function once again. And this is when it calls the second time, the size of this list becomes half of what it was before. So when we look at if we try to count the operation or the complexity of the individual portions of this program, this is a constant runtime. Here we have constant runtime. We have a constant runtime for this operation as well. The call to these functions seem constant because we are just making a call by sending it a slightly smaller or half size list once again, but making a copy of the list actually is linear complexity. So this portion over here is not constant, and that's where our complexity will originate from. So in this in this implementation, we are saying that we have to do log n bisection search calls because we are dividing the list by half every time. But within each of those, we have a linear complexity of making the copy of a list, which would result in complexity of big O of n, which is linear. If we join them together using the multiplicative rule of complexities, we get log of n times big O of n, which is log linear complexity. And now the question is, can we do a little bit better than this? And the most expensive part of our algorithm that we saw here was making this copy. So if we think about it very carefully, yes, there is a way to avoid making that copy, and we can avoid this cost to make the copy of a list and enhance our algorithm. So let's say we design our algorithm once again, and this is the second method, where instead of making the copy of a list, we are only keeping track of the pointers within which we are searching. We won't make the copy of the list, but we would only modify these pointers in every subsequent call. Depending on that initial comparison that we did about being smaller or larger than the result that we are looking for, we move this pointer over here. We did not change the starting pointer. In the next subsequent call, we change the starting pointer to the half of the list. And we can keep on going until either we find the element or we reach a size 1 list or a size 0 list, which would result in ending of or the completion of our algorithm. And here we are still reducing the size of our problem by half every time, and we are not making the copy of a list. And this kind of implementation where we don't have to copy the list when we call the recursive function once again, but just pass it the calculation of these pointers that we identify. And this would actually result in the overall complexity of log n, which is better than n log n, and better than log linear complexity. Here's the implementation of this second method. We have bisect search 2 method here, which is receiving a list and an element that we want to search. Within that, we have a helper method. I will come back to it in a minute. And the first thing that we are checking again is whether the length of list is 0, then we return false. Our element cannot be in there. But if the length is not 0, then what we are doing is we are calling our helper function with the whole list, the element that we want to find, and we are passing two pointers, one for the starting point. For our first call, this would be 0, and the last element for our first call, this would be length of L minus 1. So we are passing it pointers, the starting and ending pointer for the whole list when we are calling it the first time. When we go into this search helper function, here again, we have the list, we have the element, we have the starting point and the end point, or the low index and the high index. The first thing that we have to check if the low index is same as high, which means there's only one element that we have to look at, and we are simply checking if that is the element that we are searching for. The result of this equality operator would be either true or false, which would return it whether it has found it or not found it. If that doesn't happen, that we are trying to find the middle element by taking an average of the low and high, low plus high divided by 2, using the integer division again. And then we see if the element at that point is the element that we are looking for. If yes, then return true. Otherwise, we have to check whether we discard the lower half or the upper half of that list. And for that purpose, we will either update the low or the high. And here you can see that we are calling the search helper function once again, giving it the list, the element that we want to find. And in one case, we are saying that start with the low and go to mid minus 1, because mid we have already checked here. And if that's not the case, then for the other check, for the other recursive call, we are passing it the list, the element that we have to find. And in that case, the starting point would be mid plus 1, and the ending point, search point for our list would be the existing high index. So that way we are reducing the size by half every time. We are not making the copy of the list. All we are doing is passing it these indexes, and updating the indexes is just a mathematical operation which takes constant time. And the call to this recursive call to this function would also be constant, but it would happen log n times because we are reducing the size of our problem by half every time, which eventually would result in the complexity of log n. So everything, since we are not making a copy, the recursive call would be big O of log n, and everything else is constant running time. If you multiply both of them, the resulting complexity of this bisection search using this second method would be log of n. Another very interesting example, we are trying to convert an integer to string, and this implementation also reduces the size of our problem by a factor of 10 every time. And this would also result in log I or log n complexity, depending on how many digits are present in this number I. You can go through this implementation. It's included in the slides that was given to you. It would be interesting to just see how this runs in every for every iteration. So there is a simple loop here which runs I times, but we are reducing the size of our problem by a factor of 10. So this results in a log n complexity as well. Linear complexity, we saw this in great detail in our last lecture. We looked at several algorithms that have linear complexity, and the key to this is that there are iterative loops within the implementation, and all we are doing is reducing the size of our problem by a factor of 1 or 2 or a constant number every time. Um, as opposed to the log n complexity where we are dividing the size into half every time. So if the reduction of the problem is by a factor of by an integer value, then of course our result would be complexity linear. Factorial calculation with an iterative solution is an example of that. We have a simple for loop here which runs n times, and which means every time we run this, we are using up one value from the n. So we are reducing the running we are running this loop n times. We are reducing the size of our problem by n by 1 every time. And this would eventually result in a complexity of n or linear complexity. If we try to look at the recursive implementation, which looks a little bit better, more intuitive, over here as well, we are reducing the size of our problem whenever we call the recursive function. We are reducing n to n minus 1 for whichever n it received. And this would again the characteristic of a um, linear complexity class where we are reducing the size of our problem by a factor of 1 or by just one number every time. So these all of these kind of algorithms that reduce the size by 1 or even 2, they are linear complexity algorithms. Next class is log linear complexity, and when we look at there are some very interesting and very practical algorithms that fall in this category or this class of complexity. We will take a look at them in detail in our next lecture. That's all about log linear searching and sorting algorithms. And one of them, the most efficient sorting algorithm, for example, is merge sort, and we will analyze that in detail in our next lecture. Meanwhile, for this lecture, let's move on to the rest of the classes. We took a look at polynomial complexity last time, several algorithms that had nested for loops or while loops within each other, and or if there was a nested recursive call to the same function that usually results in quadratic complexity or polynomial complexity, depending on how many calls are there or in which way they are calling by reducing the size of the problem. This also, we looked at various examples in our last lecture. You can go back to that lecture and take a look at that. Meanwhile, for the rest of this lecture, we will be moving on to exponential complexity, which is the last complexity class other than log linear that we have to look at. Earlier, in one of the earlier classes, we looked at the solving of the problem of towers of Hanoi, where we said there are three spikes and we have to move certain disks from one in of various sizes to another spike. And the method to solve this was to solve a smaller problem, move all of these except for the last one to one spike, move the last one to the target spike, and then whatever we moved here back over here on top of it. So now we have a smaller problem of moving these two spikes instead of three first, and then move the last one, and then again the solving of the smaller problem of moving the two back to the last one as well. The implementation of this is where we are reducing the size of the problem, but we have to solve it twice before we can be done. And this is the inherent quality of exponential algorithms, where there are more than one calls to the recursive problem, or more than one recursive calls to the problem of a smaller size. And this kind of implementation would always lead to exponential complexity. We will take a look at a couple of examples in a minute, but before that, let's do some mathematical calculation here. We are saying that let's assume that for towers of Hanoi, for example, I said if we have to move four disks, first we have to move three to spare, and uh, and then we have to move the last one to the target, and then move the rest of the three from spare to target again. So we are solving this smaller problem here and this smaller problem here. This one is constant. So we can say that this solving the constant problem of moving just one larger spike is represented here, whereas solving these two smaller problems is taking t raised to power n minus 1 times, because we had to move four, but we moved three once and three once again. So two times t n minus 1 is the amount of time that will be taken for solving a problem of size n. Okay, if we do a simple substitution here for t n minus 1, we use the same formula and convert that into 2t n minus 2 plus 1 within the same equation. If we simplify that, we get 4t n minus 2 plus 2 plus 1. If we keep on doing this substitution of using the same relationship for each subsequent smaller problem, we can see there is a pattern originating here. So we had 2 as the coefficient of t n minus 1, then we have 4, and then we come to 8. So this is increasing exponentially with the power of 2. Eventually, we will come to this situation where our equation will look like this: the 2 raised to the power n minus 1 plus 2 raised to the power n minus 2, all the way up to the 0th power of 2. And if we try to simplify this, this is represented here with simple algebra. If you spend some time on it, you would understand. We have, let's say, a is equal to this statement that we eventually came to: 2 raised to the power n minus 1 plus 2 raised to the power n minus 2, all the way up to the 0th power of 1. If you multiply both sides with 2, this is the statement we get. If we subtract this one from this one, this is the final expression that we get, which is representing here that this results into an exponential complexity 2 raised to the power n. And why 2 here? Because we are calling the solution of our smaller problem twice, once over here and once over here. This constant 2 may be different, but as long as it is being raised to the power of n, where n is the size of the input that we received for solving this algorithm, this would always result in an exponential complexity. The last problem, probably last one for today, that we look at is the generation of a power set. This is a concept in set theory or number theory. A very interesting problem and very practical one as well, used in many different real life scenarios. Here, the generation of a power set looks like this. That if we have four elements within a list, we want to generate a power set which contains all possible combinations of all of these. So the first element is an empty set, nothing in it. Then we have all the sets with one element in them. Then we have all the sets with two elements and all combinations of that, 1 comma 2, 1 comma 3, 1 comma 4, and then everything with 2, not repeating 1 comma 2, and that's how this is calculated. Then we have every set with a combination of three elements in them, and lastly we have all four. So this represents the power set of this original set 1, 2, 3, 4. So four elements resulted into the calculation or generation of these 16 elements. And we will try to find an algorithm that does that. If we try to do it iteratively, that would be a very painful implementation, but what we will see here in a moment is the recursive implementation of this power set generation algorithm, which is very simple if we understand the concept. So within a power set, order doesn't matter. So we can organize them in a way so that we have everything with the which is we start with the empty set, then we just add one more element to it and generate some new combinations. Then we get one more element called 2 and generate all the combinations once again. Let's take a look at this in a try to think about it in a recursive manner. So we say that we want to generate power set of integers from 1 to n. And for that, what we would need to do, assume that we can generate all the power sets from 1 to n minus 1, and then just add the nth element to that set and generate some new elements. If we try to do that, what would happen? We have to call this solution of one lesser size recursively, and eventually it would come to a point where we are generating just the empty set. Okay, and then we say, okay, give me the next element, and then we generate a set that includes all the existing sets with that next one included. So we say everything that was there before, which was the empty set, and the new one is everything with one in it. So empty set with one is one itself. Now, given that this is our starting point now, the next solution would be get the next element and add it to each one of these existing sets. So that would result in 2 being added to the empty set, which is here, and 2 being added to 1, which is 1 comma 2. Now our next iteration would have this as the starting point and using 3 as the next addition element. So that would result into 3 being added to empty set, 3 being added to 1, which is 1 comma 3, 3 being added to 2, which is 2 comma 3, and 3 being added to 1 comma 2, which is 1, 2, and 3. So that way we are simply doing this same kind of operation of solving a smaller problem or a larger problem if we start from the very end in our recursive stack, and increasing the size of our result based on the previous input. So here you can see we have 2 raised to power 0 elements here, 2 raised to the power 1 elements in the second call, 2 raised to the power 3 elements in total, and the next one would generate 8 elements for us, which is 2 raised to the power 3. And every time we are increasing the result set by a power of 2. This is a very nice recursive solution to this generation of power sets. And if we try to do this iteratively, that's going to be a very painful process. Here's a simple implementation. We are saying that if the list is empty, just return an empty set. This is a list containing an empty list. Then if list is not list size is not equal to 0, then this is what we do. We create a smaller subset, which is just the last element, which is all the elements within L except for the last one. And the extra element that we want to include is just the last element. And what we are doing is for every element in that list, excluding the last one, we are adding this extra last element as part of that list. So everything that was there before, plus a new set of sets that includes that extra element. We will take a look at this in our code example as well in a few minutes. And so calling this function um, would recursively increase or create that power set for us. So if we write this recursive implementation, it's a very simple implementation. But doing it iteratively would be a very complex implementation and would take a lot of time, a lot of lines of code. So here, if we try to identify the running time or complexity, there are several constant um, constant cost statements here, except for this recursive call to the generation of subsets of a smaller list. And every time we do it, we have to call this generation of subset. But every time it is generating everything that was there before, it was generating a new set with while including the next element within the set. Now, the size of this smaller list increase by, as we saw here, by a factor of power of 2. 1, 2, 4, and 8. So generating that would actually result in 2 raised to power k cases for any size k list that we are dealing with. So if we try to deduce or find out the complexity, it is the same kind of mathematical calculation here. And eventually you would find out that in addition to any constant calls that we are doing, there were 5 constant runtime calls over there in this previous implementation, times the size of the initial set. But the dominant term here in determining the complexity is 2 raised to the power n steps that we have to do in doing this recursive generation of the power set. So if we try to pull it all together, while looking at all of those examples, we can identify some patterns. For any constant runtime of the algorithm, the code does not depend on the size of the problem. But if we are reducing the size of our problem by half every time, then the algorithm would result in a log n complexity. If we have simple iterative or recursive programs where recursion is being called just once and we are reducing the size of our problem by 1 every time, that would always end up with a linear complexity. Log linear complexity, we will take a look at this in our next lecture. Next lecture is all about this. And in our previous lecture, we looked at nested loops and nested recursive calls, resulting in quadratic complexity. And just now we took a look at 2 common exponential complexity problems. Now, the last example that we will take a look at is iterative implementation of Fibonacci. From our previous lecture, if you remember, we did the recursive implementation of Fibonacci, which resulted in an exponential complexity. But the iterative implementation here is a lot more efficient. We are saying that there are 2 base cases. If n is 0 or n is 1, we are just returning one if otherwise we keep track of the previous and and the one before that, two elements of Fibonacci, and then we are running a loop n minus 1 times and just updating those two numbers, I and I minus 2. Um, I or two I's, which is two steps before that. And running this n minus 1 times would result in a linear complexity of big O of n. Everything else here is constant complexity. That's just simple operation. Yeah, and for a worst case scenario, this would eventually result in a linear complexity of big O of n. On the other hand, if we were trying to do this recursively, you would notice that for every iteration of this recursive call, we are calling Fibonacci of n minus 1 and n minus 2 two times within each recursive call. Which means for this one, we have to calculate this and this. And for each one of them, we have to calculate two more. And for every subsequent level of calls, we are increasing or calling 2 raised to the power I times. Okay, for the first level, one call. Here we have two calls, then four, then eight, and the next level would have 16 calls. So a recursive implementation of Fibonacci would result in 2 raised to the power n cases. We also took a look at how to make it more efficient by maintaining all of the pre-calculated or values that were calculated once in a dictionary, and then using them would have reduced this complexity down to linear for us. But in case of Fibonacci, iterative implementation is much more efficient than the recursive implementation. And this is a simple, you can argue that when we create a tree where we identify all of the values that we have to calculate for Fibonacci, the tree on the right side is always thinner than the one on the left side because we have a larger element here and the smaller one here. And so you can argue that it's not always 2 raised to the power n, but maybe a little bit less than that. But when we take a look at for a large number of n, the complexity, the way we calculate it, would still be exponential. The gain in the thinning of this tree would not be very valuable gain in this scenario. So in summary, what we are trying to do as part of the calculation or identification of the complexity class of algorithm is that we want to identify how the runtime or the cost of the algorithm grows in relation to the input that it is receiving. And we are interested in identifying or calculating that order of growth for the algorithms. And of course, when we are trying to implement, there are several choices that we can make in writing algorithms, and that would always be towards finding whether we can go towards a lower order of growth class from a bigger one. If something is being done in n square kind of implementation, can we make it n log n? Or if it is log linear, can we make it a linear implementation? And that would be our goal when making choices in implementing algorithms that we are working with. Lastly, you would notice that we are using a lot of list operations and a lot of dictionary operations within our algorithms. We want to be very clear about what the cost of those built-in functions is. In some cases, lists are better, while in other cases, dictionaries are better. Of course, dictionaries give us a little bit more concrete functionality in terms of their storage and accessing. But if you want to index within a list, it's constant time. Storing length, appending to a list is constant time. When we want to check for equality or any of these operations, they all take linear time based on the size of the list. In dictionaries, on the other hand, since they are ordered, unsorted or unordered collections, when we have to index in a dictionary as opposed to the list, we have to find that element based on the key. So that complexity is linear. Storing is also linear. Similar for length, deletion, and iteration. But on average case, those might be constant complexity. But we have to take into account the worst case scenarios as well. So none of these are more than linear complexity. If we use dictionaries and lists in our implementation, if we have to iterate through them or do operations on them that result in a linear complexity, we have to accommodate that in the calculation of our algorithms. So we would end this lecture here. And as I mentioned before, in the next one, we would be looking at some very interesting searching and sorting algorithms, and a very efficient sorting algorithm called merge sort, which is log linear. That is the best that we can achieve in sorting elements. Okay, thank you everyone. See you in next class, which would be the last of this series. Bye.